Hello, welcome to today's lecture on this series of lectures on Introduction to Quantum Physics. In the past few lectures, we discussed some of the mathematical techniques that were needed to understand quantum mechanics, and also we discussed the quantum ideas that were introduced by Planck and by de Broglie. Today we will start sort of honest to goodness quantum mechanics. Topic for today's lecture is Schrodinger's equation. Very quick recapitulation of what I discussed in the last 3-4 lectures. Classically, we have particles with masses, and then radiation we describe in terms of waves, and the dynamical equation for particles is Newton's second law, and in Newton's second law, time is the independent variable and the coordinate values of the point are the dependent variables. Whereas in the case of a wave, we take it to be of an infinite extent, and wave satisfies a wave equation, that's the dynamical equation for waves. And in the case of wave equation, the coordinates as well as the time are the independent variables, and the dependent variable is the quantity which is oscillating. But typically when we use waves mathematically, we assume that they extend from minus infinity to plus infinity. But on the other hand, there are a lot of examples where you have waves which will go from here to here. A simple example is I ring a bell just once and I produce a brief burst of sound, and we know that sound is a pressure wave, so that pressure wave will start from here, and of course the wave will travel. And how to describe waves of such finite extent? So in order to address this problem, people in classical physics developed the concept of wave packets. A wave packet has a finite extent, it does not extend from minus infinity to infinity, only a limited range, and so the oscillations in a wave packet occur in a finite range of space and also in finite time. And to keep the discussion simple here, we will consider waves only in the spatial direction. We will not worry about the time dependence of wave packets. And how do you mathematically describe a wave packet? This I have discussed in the last few lectures. You consider a superposition of a large number of waves or large number of sinusoidal waves, and you superpose them. In fact, you superpose an infinite number of these sinusoidal waves, and also this infinite number, it is characterized by a continuous variable k, and so this superposition actually is expressed in the form of an integral which we called Fourier transform, and this is how we construct a wave packet as an integral of an infinite number of ordinary sinusoidal waves. And when we take the Fourier transform of such a wave packet, we find that the Fourier transform is also a wave packet, but it is a wave packet in the variable k rather than in the variable x. And this was the important discussion I did in the last class. You take any arbitrary wave packet, and so the wave packet has some extension delta x, some spread in the space delta x, and its Fourier transform is also a wave packet, and it has some spread in the variable k, which we call delta k, and the product delta x times delta k is always a number of order 1. This is an important mathematical theorem, and in fact one can also show that this product takes the minimum value half when the wave packet is a Gaussian. As I mentioned at the beginning of the lecture, all this is in classical physics. We haven't introduced any quantum idea in the discussion I did over the last few slides. The quantum comes in when we want to describe the properties of radiation and also the properties of massive particles like electrons. Planck hypothesis and Einstein's explanation of photoelectric effect, both of them require that the radiation which was thought of as waves should have particle properties, and the electron diffraction experiments showed that electron, which we think of as a massive point particle, actually has wave-like properties as prescribed by de Broglie. So the simple solution is we borrow the classical concept of wave packet and describe both radiation as well as electrons by wave packets. It sort of makes perfect sense. We want localized properties because a point particle, we assume, is reasonably localized and it has some position and some momentum, and in that sense the wave packet, it has some reasonably well defined position in terms of its average position, and it also has some reasonably well defined momentum because it has the Fourier transform has some average value of k, and by de Broglie hypothesis we can ascribe a momentum p to the wave packet given by p equal to h cross k. So in that sense the wave packet has these particle like properties. It has a reasonably well defined position and a reasonably well defined momentum, but it is made up of waves, so it has the wave properties also. So we have the best of both worlds, so to speak, and we make an attempt to describe these quantum objects, both radiation as well as electron, using wave packets. And since we introduce this quantum relation p is equal to h cross k, the uncertainty relation of the wave packet delta x times delta k greater than or equal to half now becomes Heisenberg's uncertainty relation delta x times delta px greater than or equal to half. Now all that is a preamble, and now we come to sort of the real crux of the matter. And what is it that we want to do? I mean, the great advance that took place in physics due to Newton is he wrote the first dynamical equation F is equal to ma, based on which one could tell how a particle which is here with some initial position and final position and some forces acting on it, how it moves from here to here. So one of the important questions we address in physics is, given an initial position of a particle or a wave or electron or radiation, what will happen to it at a later time? To answer this question, we need dynamic equation satisfied by that electron or by that radiation. I mentioned at the beginning of this lecture that for point particles, such a dynamic equation is Newton's second law in classical physics, whereas for waves it is the wave equation. But now we are trying to describe these particles these objects, not particles. We are trying to describe electrons and photons which have quantum properties. So we need to come up with a quantum dynamical equation. How do we come up with that? The first advance along this direction was made by Heisenberg in 1925, and it was sort of, he did this by imagining the position coordinate to be an infinite dimensional matrix and the momentum also to be an infinite dimensional matrix. What are these infinite dimensional matrix? How do they look? It's all very confusing, and I don't know how many people actually understood Heisenberg's arguments, but since Heisenberg used matrices to develop his quantum dynamical equation, people called it matrix mechanics. But one reason to believe Heisenberg is that using his matrix mechanics, he could derive the expression for energy levels in hydrogen atom, the same expression that Bohr derived by assuming the quantization of angular momentum. The exact same equation Heisenberg also was able to derive using his matrix mechanics, but as I told you, people were totally confused about these infinite dimensional matrices. A year later, Schrodinger came up with a completely different formalism. He derived first he introduced a quantity called wave function into physics. This is a complete break compared to what we had in classical physics, and he combined some aspects of advanced classical mechanics which goes under the name Hamiltonian dynamics. He borrowed some concepts from Hamiltonian dynamics and combined it with some inspired guesswork, and he produced a wave equation which is satisfied by this wave function that he introduced into physics. And since Schrodinger's equation, it's not the wave equation of the classical physics, but it has some similarities. So the Schrodinger formalism is called the wave mechanics, and the function he introduced in this wave mechanics, people call it the wave function. And using his wave mechanics, Schrodinger also derived the energy levels of hydrogen atom. So in that sense, Heisenberg and Schrodinger both got the correct answer, but Heisenberg talked one type of language and Schrodinger talked a totally different type of language, and then question is, who do you trust? Well, the answer was given by Schrodinger shortly thereafter. He actually was able to show that Heisenberg's matrix mechanics is actually mathematically equivalent to the wave mechanics that Schrodinger developed. So, in that sense, that part of the question is settled, but certainly I would say ever since the days of Schrodinger, people preferred to use the Schrodinger formalism rather than Heisenberg formalism for the following reason. Schrodinger equation, the equation that Schrodinger wrote down, which is satisfied by this wave function, it is a partial differential equation. Now, ever since Newton, physicists have studied partial differential equations, and it's part of a physicist's training to learn how to solve various different partial differential equations. So, that's why the language developed by Schrodinger is much more familiar to most physicists than the language that was developed by Heisenberg. Therefore, ever since Schrodinger wrote down the Schrodinger's equation, people essentially used the Schrodinger formalism, and Heisenberg formalism is used only for certain special problems. Now, how did Schrodinger get his equation? Well, to some extent it looks like this cartoon. So, you have a lot of mathematics on the left hand side, lot of mathematics on the right hand side, and in the middle there is a statement, here a miracle occurs. It's almost like that the way Schrodinger got his wave equation. He knew he had to get a wave equation, and he sort of used some inspired guess to get that wave equation. Let's see. I put the derivation of Schrodinger's equation, but derivation in quotes. So, Schrodinger's equation cannot be derived, just like you cannot derive Newton's second law. Newton's second law is the mathematical statement of a very large number of experimental observations. In some sense, Schrodinger equation also has a similar status. Schrodinger used, as I said, some inspired guess to write down the equation, and it is applied to a whole class of problems, and the predictions from Schrodinger's equation, they match the experimental observations very well. So, that is why we believe Schrodinger's equation, but we cannot derive it from any first principles. But to give you this hand waving argument about how Schrodinger, some of the thoughts you can say that Schrodinger had, let us take a free particle of mass m. So, it has some speed v, so it has momentum p, and it has kinetic energy E is equal to p square by 2m. Now, let us assume that we are describing this particle using a wave packet. So, and this particle obeys Planck's quantum relation and also de Broglie's quantum relation. So, the energy E is equal to h cross omega, and the momentum P is equal to h cross k. So, I have energy and momentum, and using the quantum relations I replace them with angular frequency omega and wave number k, which are the properties of the wave which makes up the wave packet. So, from this we have energy is equal to h cross square k square by 2m, or omega is equal to h cross k square by 2m. And instead of constructing a full-fledged wave packet, let me just write the wave as e power I kx minus omega t to keep the algebra simple. Now, I have this function psi, which is a function of x and t. I take the partial derivative of it with respect to t, I get minus I omega times the function itself. I take the partial derivative of the function with respect to x, and I get ik times the function itself. And you can see that these two partial derivatives, they satisfy the relation IH cross partial derivative of psi with respect to time plus h cross square by 2m times second partial derivative of psi with respect to x is equal to 0. So, we find that the wave function, the simple minded waveform that we took, 8, which is some arbitrary constant, times e power I kx minus omega t, that satisfies the equation IH cross d psi dt plus h cross square by 2m d square psi by dx square is equal to 0, and that equation is equal to the energy momentum relation h cross omega is equal to h cross square k square by 2m. So, this is the key point, this is the inspired guess that Schrodinger had. Energy is related to the partial derivative of the wave function with respect to time, and momentum is related to the partial derivative of the wave function with respect to x. So, this is the key insight that Schrodinger had, and as you see in this example, when he applied this insight to a simple wave function given by a times e power I kx minus omega t, he was able to get the corresponding energy momentum relation for a free particle, that is E is equal to p square by 2m from this equation. We talked about something very simple minded wave function, which is not a wave packet. So, now let us see what happens if we have a wave packet. So, let us assume that the psi x of t, or rather x comma t, is integral of the coefficient a of k times e power I kx minus omega t summed over, rather integrated over all k. This is how we constructed a wave packet before, and we use exactly the same prescription, and now we demand that this psi x comma t also should satisfy the differential equation that was written down by Schrodinger. So, we evaluate the partial derivative with respect to time, and we evaluate the second partial derivative with respect to x, and if we do so, we get the equation at the bottom of the slide, integral a of k e power I kx minus omega t, the whole thing multiplied by h cross omega minus h cross square k square by 2m dk, this whole integral is equal to 0. So, the equation only says the integral is 0, that is integral we think of it as sum of a large number of things, and what it is saying is the sum of all these large number of things is equal to 0. But now we will make the claim that the integral is 0 only if the integrand is 0. Why is that? Well, for which you need to understand some important properties in Fourier analysis. In particular, if I have two functions e power I k1x and e power I k2x, then the theorem says that there is no way I can write e power I k2x as a linear function of e power I k1x. The mathematically technical term is that these two functions are linearly independent. So, one is not proportional to another. In such a situation, these set of functions e power I kx, where k keeps changing, these set of functions are all linearly independent of each other, which means that I cannot cancel the contribution of one value of k with another value of k. So, because of which I can argue that the integral is 0 only if the integrand is 0. And integrand 0, there are two parts, a times e power I kx minus omega t, and then the quantity in the square brackets h cross omega minus h cross square k square by 2m. If I want a non-zero wave packet, I must have a e power I kx minus omega t non-zero, which means that the integral will vanish only when h cross omega is equal to h cross square k square by 2m, that is when the frequency and the wave number satisfy the energy momentum relation of the corresponding classical particle. So, this is how we try to understand how a free particle of mass m moving with momentum p, how Schrodinger's equation describes its motion. Schrodinger's equation, that is that partial differential equation I wrote, IH cross d psi dt plus h cross square by 2m d square psi dx square, that is the partial differential equation which is the Schrodinger's equation for free particles. And this equation, by the rules of quantum mechanics, is imposing the condition on the particle that its energy is equal to p square by 2m, that is it should satisfy the energy momentum relation of a free particle. So, that is how, this is of course an extremely simple example, but that is how the Schrodinger's equation is combining the quantum principles and determining the energy momentum relation for a free particle. So, this is the prescription given by Schrodinger. You take any system, it will have of course energy and momentum, and he prescribed that you replace the energy by the differential operator IH cross del del t, and you replace the momentum also by a differential operator minus IH cross del del x. This is the prescription that Schrodinger gave for to solve to generate the dynamical equation for any system, the quantum dynamical equation. So, for any object we have the relation energy is equal to kinetic energy plus potential energy. So, I replace the energy by IH cross d psi del t, and I replace the momentum by minus IH cross del psi del x, and therefore the kinetic energy p square by 2m becomes minus h cross square by 2m del square psi by del x square. And typically we assume that the potential depends only on spatial coordinates. So, the potential term is V of x multiplying psi of x t. So, using this prescription that energy is to be replaced by the derivative with respect to time multiplied by IH cross, and momentum is to be replaced by derivative with respect to space multiplied by minus IH cross, Schrodinger derived his Schrodinger's equation. Now, how did he get this prescription? Energy is to be replaced by IH cross ddt, momentum is to be replaced by minus IH cross ddx. How did he get these prescriptions? Well, some input actually is coming from this advanced classical mechanics called Hamiltonian dynamics, but certainly putting those factors IH cross is a inspired guess by Schrodinger. And so far I have talked about Schrodinger's equation in one dimension, but in principle we can extend this to 3 dimensions in a very straightforward manner. In 3 dimensions, momentum of course is a vector, so therefore we have to associate a vector operator with momentum, and a vector differential operator is well known in classical physics. It is called the operator del, and it is given by this inverted triangle. So, we identify the vector momentum with the operator minus IH cross del. Del is defined to be the unit vector in the x direction times partial derivative in x direction plus unit vector in the y direction times partial derivative in y direction plus unit vector in the z direction times partial derivative in the z direction. And the 3-dimensional Schrodinger's, now my wave function psi, it is a function of the position vector r and t, and the 3-dimensional Schrodinger's equation I have written down. It is IH cross times del psi del t is equal to minus h cross square by 2m times this operator del dotted with itself acting on psi plus V, the potential, which is now depends on the general position vector r psi, and the operator del square, it is called, it has a formal name, it is called the Laplacian operator, and it is equal to del square by del x square plus del square by del y square plus del square by del z square. Now, let me come back once more to this problem of a free particle and describe the problem of how to see the motion of a free particle using Schrodinger's equation. Previously, I talked about a wave packet where A of k is some arbitrary function, but now let me assume a explicit function for this A of k. I take it to be a Gaussian function. The reason I take it to be Gaussian is because the Gaussian functions, they have a lot of nice properties as far as their wave packet description is concerned. So, I take it to be a Gaussian function involving two constants c and alpha. The form is written there. We take this A of k and substitute it and construct the wave function, which is equivalent to saying construct the wave packet at t equal to 0. So, psi x at t equal to 0 is integral k going from minus infinity to plus infinity A of k e power I k x dk. I am putting t equal to 0, so the omega t term is not there, and I have that following integral, which you can do by completing the squares in the exponent, and you can look up the integral in any table of integrals. You can also do it by hand, which is not very difficult, and if you do so, you get an explicit form for psi x of 0 equal to c times e power minus x square by 4 alpha square. So, you have the wave packet or the wave function at t equal to 0, and its spread delta x is alpha, and you can look at the A of k, which is also a Gaussian, and its spread delta k you can work out. It turns out to be 1 over 2 alpha, and that is delta k. And for Gaussian, we said the product is minimum. You find delta x times delta k is equal to half, which will lead to delta x times delta px equal to h cross by 2. Now, by substituting this psi x comma 0 and using the Schrodinger's equation, I can work out what psi x at any time t is. The Schrodinger's equation is a first order differential equation in time. So, if I know psi x at t equal to 0, I can find psi x at any later time. And the algebra I will work out in the note, but it is some moderately involved algebra. If you do that algebra and work out what psi x comma t is, you find that it is also a Gaussian, but now the spread of this Gaussian, it has a time dependent component. So, the delta x as a function of time is square root of alpha square plus h cross t divided by 2m alpha whole square. So, you note that the spread of the wave function is increasing with time. So, let us assume that initially I have a very sharp wave function, and I will say that the wave function has become too broad to be called a wave packet if the spread at a later time is 10 times the spread at initial time. That is a rule of thumb definition I use. Then let us do the calculation for an electron which is localized within an atom. So, alpha is 10 power minus 10 meters, that is the size of an atom, and mass of electron of course is about 10 power minus 31 kilos, and if you substitute those numbers you find that in about 10 power minus 15 seconds the electron gets delocalized. Mind you, this is a free electron, not a bound electron. In an atom of course the electrons are bound and they will behave differently compared to the free electron that I am talking about here. Whereas you take a marble with a mass of about 1 gram and you localize it to about a millimeter, that is of course 10 power minus 4 meters, and you substitute the numbers and you find that the time taken for the initial spread to become 10 times that initial value, the time taken is 10 power 24 seconds, which is million times the age of the universe. So, as far as classical particles are concerned, you localize them once and they stay localized for almost ever. So, there is no question of their wave packet spreading, whereas for microscopic particles this problem of the wave packet changing with time is something very important which we have to worry about, and in fact lot of calculations deal with the problem of how the wave packets change with time when you try to manipulate them with some external probes. The Schrodinger's equation that I have talked about before, this is called time dependent Schrodinger's equation because we are considering the wave function to be a function of both space and time, and there is an explicit time derivative sitting there. But quite often we are interested in what is called time independent solutions to Schrodinger's equation. Why is that so? Well, for the same reason why we sort of take the hydrogen atom problem to be a benchmark in quantum mechanics. If you calculate the energy levels of hydrogen atom, then you can explain the spectrum of hydrogen atom, and as Bohr has pointed out, there are certain energy levels in hydrogen atom which are absolutely stable, and I shouldn't use the word absolutely stable because transitions do take place between them, but these orbits, the Bohr orbits, they are stable orbits. If a electron happens to be in a stable orbit, it will not radiate energy, it is stable in that sense. So, we are interested in finding such orbits, and the existence of that orbit, it does not depend on time. So, we try to find solutions to Schrodinger's equation which are independent of time. So, how do we do that? Well, we again appeal to important theorems in differential equations, and a very important theorem is, given a differential equation and corresponding boundary conditions, the solution to that differential equation is unique. This is also the theorem that we use in solving problems with Newton's second law. We have Newton's second law, which is a second order differential equation. We have initial position, we have initial velocity, then the motion for the rest of the time is absolutely fixed, it is unique. Similar concept here. We have a differential equation, we have the boundary conditions. That means that the solution to that differential equation is absolutely fixed, no leeway allowed. Now, you may get this solution through some systematic analysis, or you may guess the solution, but a solution you get by guessing is as good as a solution you get by systematic analysis, because there is a unique solution. So, using this theorem, we try to solve the time dependent Schrodinger's equation by saying that the wave function which depends on both x and t, actually the x dependence is in one function and the t dependence is in a totally different function. So, we write psi x comma t as psi f x, one function carrying only the x dependence, times phi of t, a second function carrying only time dependence. This technique is called separation of variables, and it is widely used in mathematics to solve problems involving partial differential equations. If we substitute this in the time dependent Schrodinger's equation, you have on the left hand side IH cross d phi dt. Now, this is a total derivative because phi is a function of time only, multiplied by psi, whereas on the right hand side you have minus h cross square by 2m d square psi dx square, again total derivatives because psi now depends only on x, plus v of x psi x multiplied by phi of t, and we divide this whole equation by psi x comma t, which we assume it to be non-zero. Then on the left hand side you have IH cross d phi dt divided by phi, and on the right hand side you have 1 over psi of x times that term in the square brackets. The left hand side is a purely function of time, there is no spatial dependence, and the right hand side is purely a function of x, there is no time dependence. So, if I say some function of time is equal to some other function of x, how can that be? It is possible when both functions are equal to a constant, only then it is possible. Otherwise, the left hand side is varying with respect to time and the right hand side is varying with respect to x. So, how can both be equal when there is a one kind of variation on the left hand side and a different kind of variation on the right hand side? So, the equality is possible when both left hand side and right hand side are equal to a constant. So, we impose that and we take the constant to be the energy. Then we have I h cross d phi dt is equal to E phi, and we can easily solve this equation and we get phi of t is equal to exponential minus I E t by h cross. Now, we look at the spatial part and equate it to psi, and if we do so, we get the equation minus h cross square by 2m d square psi by dx square, where these are total derivatives, not partial derivatives, plus v of x psi of x is equal to e times psi of x. So, now I have a second order ordinary differential equation with this constant E, and I try to solve this equation subject to the appropriate boundary conditions, and we will find that the boundary conditions actually impose constraints on the values that E can take. We will see examples of it in the next few classes, but the solutions to this equation, which is called time independent Schrodinger's equation, because now this equation has no time dependence. This time independent Schrodinger's equation, its solutions are called stationary states, and these are the, for hydrogen atom problem, these are the stable orbits that Bohr described. And I mentioned before, this equation has solutions only for some discrete values of E. For other values of E, this equation does not have any solution. So, those solutions are called stationary states, and once we calculate the wave function for this stationary state, its time dependence is trivial, which we have already calculated, and it is given by the spatial wave function multiplied by exponential minus I et by h cross. Why are they called stationary states? In order to understand that, we need to understand the physical meaning of this wave function psi, which is given through what is called probability interpretation. We will deal with in a later class. So, for the moment, don't ask why it is called a stationary state. Take it for granted that that's what it is called, and this stationary state is the same as the stable orbit of the Bohr atom. The discussion so far, I did it for Schrodinger's equation in one dimension, but in 3 dimensions a very similar discussion will take place, and the time independent Schrodinger's equation in 3 dimensions is minus h cross square by 2m times the operator del square acting on psi plus v times psi is equal to E times psi. So, this equation is going to be our bread and butter equation, and in the next class I will apply this equation to a very simple but non-trivial problem, and that will show all the important features that a typical quantum mechanical problem shows, and then we will discuss this probability interpretation. What is the physical meaning of psi? We will discuss that, and then we will tackle some slightly more complicated problems. So, thank you for joining us today, and please join us for the next week, where we try to solve some problems involving this time independent Schrodinger's equation. Thank you.